In the previous lecture, we've discussed very briefly the concept of hierarchical designs. Inside the hierarchical design, there's a very important component that we have already talked about called functional blocks, with which you can enforce hierarchical design and then build more complex circuits. In this video, we're going to further discuss the topic of functional blocks and introduce some very basic ones. A quick review on what we've done so far. We have the 5-step systematic designing procedures, where we have specification as writing the specification for the circuit. Again, this is usually supplied to you when you're trying to solve a problem. Next up, you have formulation, which essentially transforms the specification into truth tables or Boolean expressions. Step 3, optimization, is where you transform your formulation into simpler designs, and in terms of using hierarchical designs, if you know what kind of technology you have available to you, optimization can also take into consideration of the technology you have. And in step 4, technology mapping, you take whatever it is you have obtained from optimization and use the technology you have to implement them. It is very important to note that certain technologies will only be available to you at the step of technology mapping. So in cases where you want to use hierarchical design, when you're doing the optimization, your hierarchical design is only half completed, and you have to first of all start with defining all of the functional blocks you need and implement them as technologies. And only until then will you know how to optimize the overall circuit. So in certain cases, it is possible that you would need to go back and forth between optimization and technology mapping, depending on the circumstances at hand. And finally, you have step 5, verification, which involves checking the overall design against the specification of your circuit to see if it actually meets your desire. We've also talked about hierarchical design. Again, the principle of hierarchical design is to divide a complex design into smaller functional blocks. The smaller functional blocks should be slightly easier to design on their own, and then together they can be assembled to solve your final problem. And of course, each of the functional blocks that you design, you can apply the 5-step designing procedures for each of these blocks. It's just that in this case, you will need to write down the specification for them individually. And the already designed functional blocks can be easily reusable, and the basic idea is when you reuse existing functional blocks, it makes it easier and more efficient for you to implement more complex circuits. So, in today's lecture, we're going to introduce some very elementary combinational logic functions or functional blocks that you can use everywhere. Most of them are just different terminologies applied on pre-existing concepts that you have already seen, such as value fixing, transferring, and inverting. I think the only new stuff over here in this video is the enabler. So let's take a quick look. Over here, we find a definition for value fixing, transferring, and inverting. Value transferring is referring to the functional block where you supply a constant value to a specific wire. So in terms of mathematical denotation, this would be simply assigning the value of 0 to specific function or wire f, or a constant 1 to a wire f. And that's it. That's really just all there is. Transferring is a similar concept, but it refers to the operation where you are assigning a new value for a variable from another variable. So let's say you have an existing variable carried on a wire. It has certain values, and you want to give this value to another wire or another variable. Transferring is the operation you're going to need to do over there. And finally, we have inverting, which essentially just inverts the value of a variable carried on a specific wire. Now, to implement these three different functions inside LogicWorks, or to draw them down in circuit diagram, this is roughly what it looks like. For value fixing, you have a few different options when you're drawing this. On the left-hand side, you have what you would do if you're doing it by hand. You simply write down the number 1 or 0 and then connect the number to a specific wire. And you're essentially done. You have fixed the value onto a wire by giving it a constant. Right in the very middle, this is something that you would likely be seeing inside LogicWorks. This is referring to using the actual physical components to assign values instead of just writing down the mathematical circuit diagram. On top over here, you have VCC or VDD. These sources would generate a constant voltage in a high voltage area, which would result in this value being interpreted as positive. Inside LogicWorks, you can find this as a plus 5 volts circuit component. You can directly use, take and use, I believe, from Pseudo Device Library. On the bottom over here, we have our trusty friend, the digital ground. And the digital ground will provide you with a voltage always in the low voltage area. So this is considered giving a constant of 1 or 0 to a wire, and that is called value fixing. On the top right corner, we have value transferring. Value transferring doesn't need much more explanation. It is just connecting two different wires together so that the value carried on the source side can be transferred to the target side. Say we have a value carried on wire X, and we want to assign the same value to another wire F. You would simply connect these two together. X is on the input side and F is on the receiving side. And finally, you have inverting. Again, you have X on the input side and then F on the output side, where F is essentially receiving the inverted value of X. Another very important concept that we will need to discuss over here is the concept of using vector denotation. Inside LogicWorks, you have already seen this in the previous tutorials. This is similar to buses. A multi-bit function is essentially a function such as a function f over here. You would obviously realize that a function f would would take certain amount of variables as input. In most cases, the functions that we've seen so far only generate 1 bit of output, either 0 or 1. But certain functions, such as arithmetic functions, might actually generate n-bit output, and sometimes it can be cumbersome to draw all n bits separately on different wires. What you can do instead is you can group them up into a single wire and denote them using a vector. For example, in this example, we have declared a vector f. The vector f has values from n-1 all the way to 0. The column over here essentially means from certain value all the way to certain value. So you can see over here, this is equivalent to f n-1, n-2, all the way to f0. Each of the f sub I is essentially a 1-bit output function. One of the examples that you have already seen before is the curtain control circuit. The curtain control circuit we've done in the past has 3 different output ports, and you can combine the 3 output ports into a vector by saying, okay, we have a 3-bit wire. This 3-bit wire has the first bit representing the value for the motor 1, the second bit is for motor 2, and the third bit for the light control signal. To draw the circuit diagram for a bus or a bunch of wires denoted in vector denotation, this is what would happen if you do not use the vector denotation. You have 4 values on the left-hand side, and they're being transferred into f on the right-hand side. What you can do over here is you can combine them all together to form a thicker line. It is important to note that f on the right hand side is no longer just one bit. F on the right hand side is a vector of dimension 4, which means f actually carries 4 different 1-bit values. The exact dimension has to be noted on the thicker wire when you're drawing this by hand, although in this course, since everything is online, we don't actually require you to draw this by hand. In LogicWorks, you can always just use new Breakout without much concerns to the manual things. On the left hand side, it is also important that you correctly label all of the input wires that is being combined into the bus. And as our conventions, we always put the most significant digit on top. So the first bit is going to be 0, the second bit 1, the third bit the value of A, and the fourth bit the value of not A. By using a multi-bit function instead, for example, if you're carrying this 4 bits of value, say through a long distance inside your circuit diagram, you will no longer need to draw 4 separate wires. Just one thick wire would be sufficient to denote that, okay, this is coming from one source and you're transferring it to another place. Now, branching out and taking specific values from the wire is also very simple. For example, you already declared a thick wire on the left-hand side, which contains 0, 1, A, not A, on a single bus. On the right-hand side, if you want to take a portion of values from this thick wire, you can do so by doing branching. First of all, you start by drawing the thick wire, and then when you do branching, you need to specify the exact indices of values you're taking. So in the right top right corner, we have denoted over there between the thick wire and the thin wire 2, column 1. This means we're selecting indices from 2 all the way to 1. And that's how you get the output f sub 2 all the way to f sub 1. And this forms a new vector of dimension 2, which is also noted over here. This line is a little bit thinner than the 4-bit thick wire on the left, but it's still a vector and it's still a bus. On the bottom right-hand corner, we have selected a few different indices. We have selected indices 3 and then 1 all the way to 0. So this would provide with us a selection of values f sub 3 and f sub 1 and f sub 0. Again, this is also denoted in the right-hand side as a 3-dimensional vector, or a bus with 3 distinct values in them. This is how you do branching. And again, numbers 2 and 3 over here refers to the exact dimensions of the branched out buses. And the exact indices are selected also using this format, separated by comma. The final important concept in this video is something called an enabler. An enabler essentially implements the transferring function, but with an additional en, enabling signal, acting as a switch. The general principle being that if en equals 0, it doesn't matter what your other input x is, your output is always equal to 0. On the other hand, if en is 1, then the output f would equal to the value of input x. To implement such an enabler, we can simply use an AND gate, let's say. By combining an AND gate and your input x and the enabling signal en as input, it essentially has the same truth table as the enabler. So this is one of the most common ways to implement an enabler. The usage of a function such as an enabler is in cases where you want a master switch. One such example, let's say you have a building with 4 different individual lights from f sub 3, f sub 2, f sub 1 to f sub 0. And each of the lights can be controlled by individual switches, S sub 3, S sub 2, S sub 1, and F sub 0. Obviously, in separation, the individual switches should be able to control the individual lights. So S sub I, the switch, will control the light of F sub I. And what happens in a lot of the buildings is that you will also have a master switch. The master switch can instantly turn off all of the lights just by changing one signal. You can very easily implement this function by using the enablers, an array of enablers, to be more exact, on each individual switches and light pairs, like so. In this case, if En signal is 1, then F sub I would equal to the value of S sub 3, effectively providing the switches with the ability to change the output value F to control the lights, essentially. But when the En signal is turned to 0, all of the AND gates will be forced to output 0, which in effect turns off all of the lights regardless of the input from S. This is one of the most useful cases to utilize an enabler to have a master switch. And of course, on the output side, you can denote all of the outputs using a multi-bit function, hence the vector denotation. And that summarizes this video here. Thank you.